Our story following the search for the atom begins in 1803 with English chemist and physicist John Dalton. During his studies on meteorology, Dalton was perplexed by why water and air could exist as independent gases in the same space, while obviously solid bodies couldn't. Through more experimentation with gases, Dalton produced a chart of elements with their masses and symbols. His greatest contribution to science, however, was the atomic theory. This theory had 5 main assumptions. First, all matter is made up of tiny spherical particles called atoms. Second, all atoms are indestructible and unchangeable. Third, all atoms of the same element have the same properties. Fourth, when elements react, their atoms combine in simple whole number ratios. Lastly, when elements react, their atoms can combine in more than one whole number ratio. Although Dalton's discovery was huge in the scientific world, his findings would only mark the beginning in a long journey of scientific discovery. 100 years later, scientist J.J. Thomson of Cambridge University was experimenting with cathode rays and discovered that they could be deflected by an electrical field. From this, he deduced that the rays were made up of tiny negatively charged particles, 2,000 times smaller than hydrogen. He named these particles corpuscles. Contrary to Dalton's beliefs, he concluded that atoms were divisible and they were made up of these particles. His findings, Thomson produced a plum pudding model in which the negatively charged corpuscles floated around in a positively charged pudding. However, his model did not have conclusive evidence for where the electrons were and where the positive charge came from. His research would be continued by his colleague, Ernest Rutherford. To find the distribution of charge in an atom, Rutherford performed his soon-to-be famous gold foil experiment. In this experiment, Rutherford shot alpha particles at a piece of gold foil. According to Thomson's model, the particles should bounce off the gold foil at less than 90-degree angles into the detection screen. To his amazement, Rutherford found that the alpha particles usually went straight through the gold foil, but sometimes hit a massive solid object and bounced off at random angles. He concluded that the atom must be mostly empty space. In his planetary model of the atom, Rutherford stated that the atom had a positively charged nucleus in the center with electrons orbiting around it. Although this discovery was monumental, a new question arose. What comprised the nucleus? This question would be answered by Rutherford's colleague, James Chadwick. In his experiment to find the neutron, Chadwick shot radioactive particles at beryllium in a vacuum chamber. Due to the radiation, the beryllium structure changed, and it released neutrons. These neutrons were then directed toward a block of paraffin wax. Because the protons were knocked out of the wax by the neutrons upon collision, Chadwick decided that these two particles had similar mass. It then became apparent that the nucleus was made up of a combination of protons and neutrons. However, in his Nobel Prize speech in 1932, Chadwick stated that it would take much longer to determine what made up neutrons and protons. This mysterious puzzle would be solved with the invention of particle accelerators in the 20th century. Particle accelerators, otherwise known as atom smashers, used electromagnetism to propel particles into each other at near light speed. The particle accelerators contain mass amounts of high-tech equipment in order to record the collisions of the atoms and to propel them at such colossal speeds. Onlooking scientists recorded what particles were produced after the collisions. With this data, they came up with the standard atomic model. Part 2. Standard atomic model consists of 3 main sections. Leptons, elementary particles such as the electron which do not hold the nucleus together. Quarks, which make up hadrons such as protons and neutrons. And bosons, particles that carry the 4 fundamental forces: gravity, electromagnetism, weak force, and strong force. Before even venturing into the dark depths of the atom, we must know what constitutes its center. The nucleus is made up of quarks. There are 6 which come in 6 different flavors: up and down, top and bottom, charm, and strange. When forming particles such as protons and neutrons, quarks occur in combinations of 3, and they are held together by a gluon, which is a particle that carries the strong force. One of the particles in the nucleus is the positively charged proton. It is made up of 2 up quarks with a plus 2/3 charge and 1 down quark with a minus 1/3 charge, giving it a plus 1 charge. Remember, the quarks are held together by a gluon through the color force. They contribute to the organization of the periodic table. Each element is ordered in ascending order based on how many protons it contains. This is called the atomic number. The second particle in the nucleus is the neutron. The neutron is made up of 2 down quarks with a negative 1/3 charge and 1 up quark with a positive 2/3 charge, giving it 0 charge. Neutrons are important because, contrary to Dalton's third law, atoms of the same element, but with different numbers of neutrons, form isotopes. These isotopes give elements an average atomic mass, such as lithium's 6.9. These 2 particles form the nucleus, and are held together, once again, by the strong force. If the strong force were not to exist, the nucleus would look a little something like this. The electron is a small elementary particle that orbits around the nucleus. It has a negative charge and is part of the group of leptons. The electron can spin in a clockwise manner or a counterclockwise manner. The electron's orbit and placement around the nucleus is determined by the 4 quantum numbers. The principal quantum number n describes the size and energy level of each orbital. The angular quantum number L describes the shape of the orbital. These 4 orbitals are sphere, polar, clover leaf, and as L's value increases, the complexity of the orbital does too. For each value of L, the orbital is given a specific letter symbol. The magnetic quantum number m describes the orientation of an orbital in the space of an atom. Besides the s orbital, all other orbitals have different values for the m number. Since each orbital contains 2 electrons, the spin quantum number s helps to determine which electron in the orbital is spinning in which direction. However, as always in nature, there are laws. Quantum numbers have 5 laws governing their properties. Not only do quantum numbers help describe the shapes and energy levels of orbitals, but they also combine in specific patterns to form shells and subshells. This combination can be shown using electron configuration. When 2 orbitals have the same principal quantum number, they form a shell around the nucleus. Orbitals within this shell with the same angular quantum number form a subshell. The shell and subshell to which an orbital belongs is described by a 2-character code. The first character is the principal quantum number. The second is the value of the angular quantum number. In order to utilize this code, we must follow 2 principles. According to Aufbau principle, electrons are added to an atom one at a time, starting with the lowest energy orbital until all of the electrons have been placed in the appropriate orbital. But wait! What happens when more than 2 electrons need to be added into an orbital? For example, in nitrogen, where there are 3 electrons in the 2p orbital. This can be solved using degenerate orbitals. Due to the magnetic quantum number, the p orbital is oriented in 3 different directions. Each different orientation is a degenerate orbital, which can contain up to 2 electrons. The degenerate orbitals are filled out according to Hund's rule. Electrons with the same quantum spin number are added until each orbital has 1 electron. Then, electrons with the opposite spin number are added to fill the orbital. Thus, the electron configuration of iron would look something like this.